Let's start by reviewing how base 10 numbers work. This should be a number system you're very familiar with. I think you probably use base 10 numbers pretty often, like all the time. So this is my base 10 number. Now this 2 right here, of course you know, is really the ones place, right? That's really a 2 in the ones place. This 8, of course, is really in the tens place. The 6 is in the hundreds place. And you know by now in base 10, of course, every time you go up in place value, you multiply by 10, right? 1, 10, 100,000. And of course, I can keep going, right? I can just multiply by 10 again, multiply by 10 again, go on forever. Of course, another way of thinking about this is, 10 to the 0 gives me a 1. 10 to the 1 gives me a 10. 10 squared gives me 100. 10 cubed, 10 times 10 times 10 is 1,000. So any way you like to think about it is fine. So just again to be clear, this 7, hey, that's not really a 7, that's really a 7,000 because of the position, right? This 6 is really a 600. Well, you know how base 10 works. But I think it's good to think about that before we start talking about binary. Now I'm going to write a number in binary. This is very exciting. Of course, computers use binary, and binary just has 2 possible numbers that you can write, either 0 or 1. So I'm just going to write a bunch of zeros and ones there. That is my binary number. Now it works the same way as base 10 numbers work. In other words, the position is what gives the digit its value. This is, of course, the ones place. This is the twos place. This is the fours place. This is the eights place. Are you thinking about what the next one is going to be? The 16s place, the 32s place. Very similar to base 10, except this is base 2 or binary. Every time I go up in place value, I multiply by 2, right? So I could really think of this as 2 to the 0, that's 1, 2 to the first, 2 squared, of course, is 4, 2 cubed is 8, 2 to the fourth is 16, and I can just keep going here on and on and on if I wanted to. So how do I figure out what this number is? This is a binary number. Sometimes I write a little 2 there to show that it's binary. How do I figure out what it is in base 10? Well, it couldn't be easier. I have a 1 in the 32s place. Well, that's a 32. Then I have a 1 in the 8s place. Maybe I'll keep track of it underneath. Right, I have a 0 here, so I don't really care about that. I have a 1 in the 8s place. That is 8. I have a 1 in the 2's place, that is a 2, and I have a 1 in the 1's place. So let's see if I can add all these up. That is 43. Hey, base 10. So this number up here is a 43 in base 10. Now I'm going to go the other way. Oh, this is so much fun. Now I'm going to convert the other way. In other words, I will start with a base 10 number. Let's use 43, shall we? In base 10, and I'm going to go to binary. Well, this is also pretty easy. I mean, there's more than one way to do this, but the way I like to do it, and I think this is the easiest way, is I just draw some dashes on my paper representing the positions of my bits, of my binary numbers. This is, of course, the ones place, the twos place, the fours place, the eights place, the 16s place, the 32's place, the 64 place. Well, I don't think I'm going to need anything in the 64 place because my number is only 43. So I don't even need this. But certainly, cross that out, certainly I'm going to need a 1 in the 32's place. And if I subtract 32, I can see what I have left over. Well, that looks like I have an 11 left over. So I need to make 11 out of what I have remaining. Well, I don't need anything in the 16's place, right? I only need to make 11. But I do need an 8, so that'll give me 8. I'm up to 40 so far. Actually, let me just subtract that 8, and I can see that I have 3 left. Well, I don't need anything in the 4's place, but I do need a 2 and a 1. Now, I could check it, of course. I have my 32. We know this is going to work. I have my 32 plus 8 is 40, 42, 43. Hey, that couldn't be easier. So going from base 10 to binary and from binary to base 10, that's pretty easy. Now let's look at hexadecimal. So before we start converting between hexadecimal and decimal or binary, let's just take a look at the 3 number systems here. Binary, of course, has only a 0 and 1 as possible digits, right? There's only 2 possible values here. Decimal, and of course binary is base 2, decimal has 10 possible digits, 0 through 9, right? That's 10 possible digits. Hey, decimal is base 10. Hexadecimal, well, that is base 16. And if you notice here, I go 0 through 9. Well, that gives me 10 possible values. But then it uses letters. This is actually 16 possible digit values, right? After 9, it uses A to represent a 10. It uses B to represent an 11. C is a 12. D is a 13. E is a 14. And F is a 15. And I hope it's obvious why they need to use a single letter value here as opposed to writing 1, 3, because right, if I wrote 1, 3, it would look like a 1 and a 3. Well, I want to represent it in one digit. So I hope you can remember this. Decimal, 10 possible values. Binary, 2 possible values. Hexadecimal, that's base 16, 16 possible values. And they go from 0 to 15. All right, now let's do some converting. I wrote down the hexadecimal values on the side here just so that I can remember that A is a 10 and so forth. All right, so now I'm going to write a hexadecimal number. I don't know, I'll just make something up here. How about 2AC, right? This is a hexadecimal. Hexadecimal, of course, is base 16. This is my base 16 number. So let's figure out what this is in base 10. This C, of course, is in the ones place. Just like every other number system, you start out in the ones place. Now, this is a base 16 number system, so every time we go up in place value, we multiply by 16. This A is in the 16s place. This 2 is in the 16 times 16s place, or the 256th place. This works the same as every other number system, right? This is 16 to the 0, also known as the ones place. This is 16 to the 1, or the 16s place. This is 16 squared, known as a 256 place, and I could just keep going. 16 cubed, blah, 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 blah. But let's just take this number, for example. So this 2 here, of course, is not really a 2. It's really a 2 times 256. So that's 512, really. This A is really a 10. Remember, A is 10. It's really a 10 in the 16s place. Well, 10 times 16 is 160. This C is in the ones place. Well, it's not really a C, it's really a 12 here, right? C represents 12, so this is plus 12. So this number in base 10 is, I'm just adding everything up, is a 4, that's an 8, and that is a 6. So this is the number 684 in base 10. All right, now let's think about another way of converting these values. It turns out there is a very nice shortcut, and it's actually no accident, between hexadecimal and binary, and that's why hexadecimal is used, because each hexadecimal digit really can be represented by 4 binary digits. So really, I can represent this value in binary. Let's see, a 2 in binary, that is a 0, 0, 1, 0. Why is that a 2? Well, remember in binary, that's the 1's place, the 2's place, the 4's place, the 8's place. So that is a 2 in binary. This A can also be represented as 4 binary bits here. Now an A is a 10, of course. So let me make a 10 in binary. Well, how is that a 10 in binary? Well, that's the 1's place, the 2's place, the 4's place, the 8's place. 8 plus 2 is 10. And that C, of course, is a 12, and I can also represent that with 4 binary bits there. So that would be an 1, 1, 0, 0, and that is a 12, of course, because I have nothing in the 1's or 2's place, but I have a 4 and an 8. 4 plus 8 is 12. So I just represented this number in binary. Well, that was a piece of cake. Now, of course, I could verify that this is 684 by just going through my binary number from beginning to end and realizing this is the 1's place, the 2's place, the 4's place, the 8's place, 16, 32, 64, 128, 256, 512. And if I add up 512 plus 128 plus 32 plus 8 plus 4, I will get 684. All right, I'm just going to do one more. I'm going to go from binary back to hexadecimal. And finally, I'm going to convert from binary to hexadecimal. So I'm going to make myself a huge binary number here. Oh, that's a big one. I don't know. I'm just making stuff up here. And I'll go 0, 1, 1, 1. Well, that is a big binary number. The good news is that I know that every 4 binary bits represents 1 hexadecimal digit. So I just have to think of this as a 4-bit binary number. 1's place, 2's place, 4's place, 8's place. Well, that's 4, 5, 6, 7. So this is a 7 right here. This, of course, again, 1's place, 2's place, 4's place, 8's place. So that is a 5. 1's place, 2's place, 4's place, 8's place. That's 12, 13, 14, 15. Now, of course, a 15 is an F. And then my last binary number here, 1's place, 2's place, 4's place, 8's place. That, of course, is a 14, which is an E. All right, so this is my binary number, and there I have converted it to my base 16 hexadecimal number. It is just EF57 in base 16. Now, of course, I could convert it to base 10 pretty easily if I wanted to. You know how to certainly go back to binary. I think you can convert between binary, decimal, and hexadecimal. Yes, you should be able to convert between all three. All right, thanks so much for watching.